So in this slide, I'm going to talk to you about what is meant by fully connected layer. Reiterating some of the things I already mentioned in connection with the convolutional neural network. So, for example, if you have the input as image 2, numeral number 2, then we use this filter. That these are the filters that moves around like this, and then comes back here like this, and then comes back here like this, and so on. So this filter with the ideas about the feature, what kind of features needs to be captured, whether it is based on the curve, vertical line, oval, square or circle, whatever that is implicated here, and when it goes around here, it picks up those ranges, those areas where these signals are where these signals are capturing those numerals, okay, or embedded in those numerals. So a 28 by 28 becomes a 24 by 24 size, when this is a 5 by 5 kernel, okay, because you remember 5 by 5 kernel, it's basically going over 5 by 5. So we are talking about 5. First you take the 5 and go to the next one, 5, and so on, right? So the you can also sometimes add paddings. Let's compute without the paddings right now. So 5 by 5, and then you go to another 5 by 5. So how many different 5 by 5 you can have when you move one cell at a time, right? That is 24, okay? And that's why it becomes 28 by 28 becomes 24 by 24, and then we apply a max pool of 2 by 2 matrix of the values here. This is 2 by 2, and that gives you maximum of among the 2 by 2. What is the maximum value? That is what is captured here. That becomes 12 by 12. The 12 by 12 features are different features. These could be different features on top of different images. Remember, that's why it's a very computationally intensive method. So all this for one feature, whatever that particular one feature, you compute across all the images, that these are the images, then you get so the learned feature is let's say a curve like this matters, okay, and that's this feature is supposed to capture that curve like curve like this, and that is what is run through, and all the images, those are all using max pool reduced, and then again we use another convolution, and then another max pool reduced it. Finally, when it's 4 by 4, finally it can get the final application of the max pool will reduce to a single number, and you use those single number as your inputs, okay, and those single number as inputs now can be considered as a multi-layer perceptron models, connecting it to the to the output values, in this case 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and this is basically a multi-layer perceptron model, fully connected for each of these outputs, and using softmax application you can figure out what the predicted answer for any given. Once you build the model, you can find out what is the predicted value of each of the images are. So the last max pool flattens out in the end. Last max pool in flattened layer, every filter's correlation to every part of the image is captured. Flattened layer has captured all the relevant features of the image for discrimination purposes. Since all the spatial features are captured in max pool, can be flattened layer can be mapped to either output or another dense layer. Need training weights in all the filters as well, large number of parameters. That's why deep learning neural network is a huge computational, if I may call it, as a burden, okay, but that's part of the game, okay, that's part of the game today. That's what the best thing that we can do, and which means we have to spend a lot of computational power and energy to accomplish our solution and to create our solutions. You remember with CNN we have customized extracting spatial features, so there is a cost and benefit trade-off. CNN usually is more accurate than any other deep neural network for classification, but the number of parameters grows exponentially. That means we have a higher chance of overfitting. Model may perform poorly on the test data. But generally, so far we have been accomplishing, in practical problems, as long as it is as labeled data, we are good. So that is the huge parameter. Hundreds of millions of parameters are involved sometimes. And I also want to recall this overfitting and underfitting. You remember that if I have some, these 8 points, and if I connect each one of them like this, it's a perfect model, right, in the training, but it's overfitting. It won't do well for your test data, because test data is not going to be exactly like this, right? That's why test data is separated from the training data. In the case of optimum way to do that is, this is underfitting, because there is a lot of error here. The best model is this one, which is a nonlinear expression here. And how do we find this best model? That's where the bias variance trade-off is helping us. This is the predictive error. So the predictive error goes down for the training data, but nonetheless for the validation data it will be like this, because as the model complexity increases, which means more number of parameters, more complexity is more number of parameters, and it does help to predict better, but then there is a limit to it, and this is the limiting point. For this, for a particular sample, somewhere like this, you will come across, then you stop here. That is your sweet spot. We call, we say that this is the stopping place, where you don't want to make it more and more complex. So you need to make sure that your number of parameters are only up to this, and you will do a good job with respect to testing also, because that is validation is about, this is the validation bias variance validation error curve, and that is supposed to represent the test data. So when you stop here, even the training keeps going, you are good in applying the right model for your test data. So why do we say bias variance trade-off and all those things? Because mean square error for a continuous variable, y a continuous variable, mean square error is y hat minus y bar, y hat minus y, predictive minus the actual square is the mean square error, and you can add and subtract the y bar actually. Okay, it should be y bar, so it's not y hat here, and it will result eventually variance. Variance and expectation of y. Okay, expectation of y hat is y bar, so that's where it is. Okay, so eventually you can split this into variance part of it and bias part of it. Okay, mean square error, which is the predictive error, is sum of two quantities. So if for a fixed mean square error, you cannot reduce both. Okay, so you can reduce variance. But you cannot reduce bias square, right? Or you can reduce, if you want to reduce MSC, for a given MSC, you can manipulate a little bit of this, each, but not both. That's the main point. Okay, a little bit of each if you want. So you can have a little bit biased model by allowing some amount of reduction in variance, or uncertainty in the model by reducing the bias. Okay, so sometimes we do say that best model doesn't have to be really bias is zero. Okay, because in the traditional statistical learning, and they proved that also, that you can allow some bias to have a better model. Okay, so the next concept that I want to introduce you is, there are a few other concepts I want to introduce, that is the regularization and the dropout, data augmentation, early stopping, and batch normalization. So there are two types of regularization. One is called the L1 loss and L2 loss. L1 loss says the mean square error plus the lambda times summation of absolute values of the parameters. On the other hand, the L2 loss mentions MSC plus loss function is mean square error plus lambda times summation of each of the weight square. Okay, sum of weight squares. So because you want to minimize this loss function, means you can minimize the mean square error, but if you don't put any constraint here, this is going to, after a while, if you put, because this is what your loss function now is, it's not purely mean square error. That's usually if you don't have the cost associated with the parameters, you will have only this to minimize. But we want to associate a cost to increasing the number of parameters. So that cost is summation of the parameter values or summation of the square of the parameter values. And what we are saying is that this loss will, if you continue to increase the number of parameters, the loss will not reduce, continuously reduce, even training model, okay, continuously reduce, because this is going to increase, this part is going to increase, okay, as it goes down by adding more and more parameter, which means by adding complexity. As you add the complexity, this will reduce, but this will increase. So the counterbalance, of the complexity into the loss function is this summation, lambda times, the weighted value of the sum of the parameter values, or the weighted value of some of the parameters value squares. So there are two different algorithms that are used usually, that is called L1 and L2 regularization, and you can use any one of them. Sometimes you do both and then select the best that gives you the lowest predictive error, okay. So lowest loss, and in turn the lowest predictive error, okay. So that's what this L1 and L2 regularization is about. We are regularizing it for the complexity, increasing complexity. We are regularizing it for increasing complexity. On top of it, we also want to do what is called the dropouts, okay. At every iteration, we randomly select certain neurons not to contribute to the estimates, okay. So that is what is basically a dropout. So if you say dropout rate is 0.2, then 20% of neurons will randomly be eliminated, and that way we can control the overfitting also, okay. This is similar to tree pruning. First build the model with no dropouts and look at loss versus epoch, and make sure that the error, bias variance error trade-off, bias variance trade-off is helping us to find the best model. But initially, you do the model without dropouts, and then look at the loss versus epoch and make sure it's decreasing. Then you introduce dropouts to make sure that it balances out for increasing complexity. So that's basically what I want to talk to you about today. Let's go to the next concept. Of course, now I want to introduce the next concept also, that is data augmentation. So sometimes we want to do transformations on the images. For example, you may want to rotate, shift the images. This is the image area, but that particular part is a small part. You can reduce, bring it down, bring it up, go up on the sides and move on, and then blur it, change some pixels, shift horizontally, skew it, and so on. There are many ways you can transform the data, and and that way the features are robust. In a robust way, is helping us to predict correctly the various numerals. So that is data augmentation layer in such a way that they have mean output of 0 and standard deviation of 1. Normalizing the inputs to a network helps to learn. And also we are submitting it as batches. Remember that, okay. Don't give the whole data set to train the model. You submit it as batches and then take the average of the parameter values, okay. And finally, so we talked about batch normalization. So normalize the data, input data, as well as batch process the results. So batch process the fitting method, neural network parameter estimation. If the training error is high and validation error is high, so if the training error is high and then validation error is also high, there is a high bias. So increase model complexity, train for more epochs. And if training error is low and validation error is high, there is high variance, and that means add more training data or reduce the complexity or add more training data. Data augmentation is one way. Use regularization, use early stopping. If training error is low and validation error is low, perfect trade-off, you are done with your work, okay. In summary, that's what I would like to say. In for the assignment 2, we are looking at CFAR, Canadian Institute for Advanced Research 10 data set. is a collection of images that are commonly used to train machine learning and computer vision algorithms. Okay, it's one of the widely used datasets for machine learning approach. The C pattern contains 60,000 32 by 32 color images in 10 different classes. The 10 different classes represent airplanes, cars, birds, cats, deer, dogs, frogs, horses, ships, and trucks. There are 6,000 images of each class. Okay, and the problem formulation is, you divide this into training and validation images and keep, so 20,000 training. Well, you can keep 30,000 training and 10,000 for validation, 40,000, another for 10,000 for testing. And remember, each of them is a 32 by 32 pixel, which is a 1024 pixel, valued color images, RGB, and the goal is to predict the class with high accuracy for new test data. And what data do we need? Label. We have a labeled data with reference data samples, right? So we are good. So there are 5 experiments, we want you to do. The goal is to compare deep learning neural network and CNN for CFAR. Remember, deep learning simply says you keep doing multiple layers of hidden neuron, nothing else. But then you are going to do simple deep learning neural network versus CNN, so convolutional neural network. So in all the experiments, we would hold some parameters constant. The batch size is 10,000. The number of epochs is 20. Same optimizer, same loss function of cross entropy, so that the comparisons are fair. So first experiment is do the DNN with the 2 layers, no regularization and no convolutional neural network here. Okay, it's simply a multi-layer perceptron with many layers of deep neural network. You can use as many layers as you want, but we are saying experiment 1 is only 2 layers. In experiment 2, we are asking you to do 3 layers, no regularization. In experiment 3 is now you do the CNN with 2 convolutions, and each time you are applying the max pools. Okay, no regularization. And experiment 4 is CNN with 3 convolutions. Again, for each of them you will use max pool layer and no regularization. Experiment 5 and plus is you will conduct several more experiments, redo all the 4 experiments with some regularization. So with all these 4 you can do with some regularization technique, and increase and B is create more experiments on your own by tweaking architectures and or hyperparameters. Bottom line, you need to do more than 10 experiments. Result is, result 1 is create a table with the accuracy and loss for training, testing and validation, and process time for all the models. Result 2 is report these. Okay, result 2 is take experiment 3, that is CNN with 2 convolution, extract the outputs from 2 filters from the 2 max pool layers and visualize them in a grid as images, and see whether the lighted up regions correspond to the same features in original image. Okay, so this is a very interesting exercise. Do that. Okay, and remember the Keras terminologies are: kernel means size of convolution window 3 by 3, for example. Filter means number of output filters in the convolution, horizontal, vertical, etc. All kinds of things. Channel means RGB channels or abstract versions of color. Weights of a convolution layer has the shape, kernel size, number of channels, number of filters per channel. In general, for audio, we have kernel 3, 2 channels. Example shape is 3, 2, 16. It's also called convolution 1D. For audio channel. For color image, we have convolution 2D. For video, we have convolution 3D. And these are some standard standard shapes to think about. Okay, for you to understand when to use what under these 3 types of data, that is audio, color image, and video. Okay, the model parameters, for example, if you do this, here is an example. So I take a model is model sequential, that this is building these layers sequentially, and so 128, the filter size is 128, kernel size is 3 by 3, and then strides are 1 by 1, activation is ReLU, and shape is 32 by 32 by 3. Okay, the next layer, we are max pool is 2D. We are taking 2 by 2 strides. That means 2 at a time. 2 strides, and here stride is 1 at a time, 1 cell at a time. Dropout is 30% we want to drop out, do the dropout layer, and continue to do this kind of construction of the sequential process. Convolution 2D, convolution 2D, convolution 2D, and then max pull, max pull, max pull, and then drop out, drop out, drop out, and finally we flatten. And when we flatten, we will have 384 units. And the regularization is the L2 regularization, not L1, and the lambda is, this is the lambda value, okay? Finally the dense layer has 10, the dense layer has the units 10, activation is softmax. The final layer is, the dense layer is 10 units only, right? Because 0 to, not 0, it's an image, right? So different images, 10 images. So when you do that, it will print out, like this. Here it tells you how many parameters are there, what is the shape of the output shape. So you will see the, parameters calculations are like this. Kernel shape is 3 by 3 by 3. So plus the bias, right? Plus the bias. So we have times 128 such filters. It tries different filters, right? 128 filters we are trying. So totally we will have so many parameters to pass through to estimate. And then max pull is 2 by 2. Finally kernel is 3 by 3 times 128 times plus 1, 256. So 256. And it becomes the next layer. I'm talking about this layer. For this layer, how many parameters are there? That's what this calculation is, and this calculation is how many parameters are the third layer, okay? And then fourth layer is this, and finally this one, 3072 pixels summarized to 384 features, neurons with the goal of discrimination. That's the last one. Okay, so you will get an idea about how these the parameters are calculated, and here is the example calculation for you how these parameters are calculated. And so the way we want you to write the report is as follows: organize the paper as a research report with each section answering basic questions as identified in bold type, abstract, and executive, which means an executive summary, introduction, which means why are you conducting this research, business case, problem formulation, pick out from practical life where this can be applied. Literature review, who else has conducted research like this. Methods, how are you conducting research, review research, design and modeling methods, implementation, programming, data preparation, exploration, visualization, results, what did you learn from this research, okay? Because you did many experiments, right? That's what your research is. And then finally the conclusion, so what, does it, what does it mean, what does it all mean in practical, for practical application. Exposition, and that you will talk about exposition, problem description, and management recommendations. So, create the output, HTML also, HTML walkthrough, HTML output, which is basically your notebook, output converted into HTML, which is right now, initially it will be the IPython notebook, Jupyter notebook, but you need to convert it into an HTML output. From there, you can convert it into an HTML output, walk through that. So finally, you are going to talk, you are going to present as saying what kind of modeling is relevant for us, okay? DNN or CNN, how do I do regularization? So you learn all these things, how many models to build, test validation, how can I tweak hyperparameters, what is the trade-off, what is the best accuracy can I get, exploration and experimentation. So, let's stop here. I have more things to do for you. I will talk about it later on beyond MNIST and CFAR in the next presentation. Thank you.